Hello, greetings to you all, and I hope you are all great. Yes, I'm so excited to meet you all once again, Ayeki, and I'm privileged to also lecture you on applied electricity and calculus. So, what is the objective of what I'm doing? Right, I have an objective for doing all these videos. My objective is to what is to help you get an A in calculus and also an A in what in applied electronics. So please, in order to achieve this objective, right, you also have a duty to play. You have a role. So what's your responsibility? Is to follow me diligently. So your objective is to follow me what diligently. And when I say you are following me diligently, it means that you do all what I ask you to do. All what I ask you to do. If you don't do it, frankly speaking, you're not going to like the tutorial that we are doing here, right? If I ask you to solve questions, try to solve it. I'm so happy when some people were sending me. I know that some of you two were able to do it at ease, right? Those who were struggling, some of them were sending me questions for me to what assist them. Do you get it? So if you follow me diligently, you are going to what? You are going to get an A. And when I ask you to read something through, please try as much as possible to read it, right? So with applied electronics, let's talk about applied electronics. So why do people fail applied electronics, or the reason for failure, right? There's no secret to it, right? But the students don't like reading. Students don't like reading the course. See, maybe you pick the book and you feel like reading, and at the end it seems like an abstract to you, so you don't see the need to what to read it. You only read it when there's exams or some pressure. Do you get it? So the reason why I'm making this video is to make it easy for you to what easy, right, for you to read. That's the reason why I'm trying to make all these videos. So once I make the video, it will be so easy for you to read. So as soon as you are done, please, the page that I'll ask you to read, try to read them within the week. Are you okay? Yes. So if there is a need for software simulations, I'll always add it to it. So when there's a need for software simulations, I'll always what add it to it so that you understand it. So after every section, right, you always understand, get a fair knowledge on what the concept is about, the discussion is about. Then I'll ask you to read some pages. Then once you read it, it will be so easy for you. So please try as much as possible to read what I ask you to read. Are you okay? Yes. Because with the applied electronics, it's also going to be objectives. That is 100 to 120. It's either sometimes it's 100, sometimes it can be 120 objectives. So you're going to solve 120 objectives or 100 objectives. So just psych your mind to understand. Don't memorize anything, or don't memorize to the exams hall. Once you memorize to the exams hall, you are going to struggle because they are not going to ask you to define anything. It's going to be objectives. So once you go there, you read and you understand it, then you choose the best option. Please take note. At the electrical department, they hardly set past question. Are you okay? So don't expect past question. Just understand it. Understand what we do here. And if you're able to understand it very well, you'll be able to what? To solve it if past question do not what appear in the exam. Are you okay? Yes. So today, what are you going to talk about? Let's begin. We are going to talk about the classes of materials. Classes of what? Of materials. Right? In terms of terms of what? Their conductivity. Yes, then we also talk about the band gap. Band gap. Yes. Then we will talk about what? Or we compare a semiconductor atom to what? To a conductor atom. Then we talk about the two popular semiconductor materials that are used in making electronic components. So we are going to compare silicon and germanium. So these are the two semiconductor materials that are mostly used in making electronic components. But among the two, people prefer silicon. So we'll talk about why people prefer silicon to germanium. Right. Then we'll talk about conduction electrons, conduction electrons and holes. Right. Then after that, we talk about electron hole pair. Electron hole pair. Right. Then I'll give you the reading assignments. Reading assignments will follow. Right. They will bring the lesson to a close. Are you okay? Yes. So let's set the ball rolling. So as we continue, I've classified the materials already. We have insulators, we have conductors, and we have semiconductors. What are the insulators? So as usual, we say that insulators are what? Insulators are the materials that does not conduct electrical current under normal condition. The term is normal condition. So for instance, I have wood, right? Wood is under normal condition. Do you get it? That is, if let's say I have wet wood, this might not make it a normal condition. It can easily conduct because wet wood consists of some moisture. Are you okay? And we know that water is a good conductor of what? Of electricity. So once we have that one, it can easily conduct. So it should have a normal condition. If it's plastic, it should be plastic. And sometimes if let's say you mix plastic with other materials, it can make it conduct. You get it? So when we say they are under normal condition, like they should be at their pure state, something like that. You get it? So examples include the wood, we have rubber, we also have mica. Yes, we have mica, and we have quartz. Yes, we have quartz there as a, an insulator, right? And we also have plastic, glass, we have plastic, and so on and so forth. You get it? So what about the conductor? The conductor is a material that easily conducts electrical currents. Okay. A conductor is a material that easily conducts electrical currents. Then a semiconductor is a material whose conductivity lies between. So their conductivity is between insulators and what? And conductors. Okay. This is more like the junior high school and senior high school stuff. So I'm not expecting anyone to struggle. Okay. So the next thing that we'll talk about is the band gap, which is very, very, very important. The band gap. Are you okay? So assuming I have energy flow like this, energy is flowing from what? Zero. That is the first band here. We have a band here, which is normally the valence band, right? The valence band or the outermost shell band. Any atom is having outermost shell. So the valence or the outermost shell band. You get it? And we also have the conduction band, where the electron begins to what? To conduct. So that is the conduction band. conduction band, right? Between them is what is termed as the band gap. So the gap between the conduction band and the valence band is what is termed as what? As the band gap. So electrons are normally here. This is the outermost shell of an atom. When I say outermost shell of an atom, you already know. So this is the outermost shell of an atom. So this atom is having electrons, right? So they are filled with electrons. And the electrons are always eager to move from the valence band towards to the conduction band. Okay, so the gap between the conduction band and the valence band is what is termed as what? As the band gap. So wait, those materials, right? The insulators, the conductors, and the semiconductors, right? They can be classified with a band gap. So I'll come to draw the same thing here, but quite different. Then I can group those three under insulators, and I can also group them under, how do you call it, semiconductors and conductors. So we have the conduction band here, conduction band here, and we have the valence band, that is the outermost shell band, valence band, right? Then the next one, we have it here like this. So we have the valence band, right? Let me use a different. Okay, so let me see the conduction band here. So actually, right, they are overlapping, right? They are overlapping. One overlaps the other. So they don't have, like, their band gap is not existing, right? Because they overlaps. So with these three, let me label this as I, and I. Actually, this is the energy flow from zero towards any number that you can talk about. So it's an energy line, right? So from zero to any value that you can talk about, like any value of energy. There is energy flowing up there, from down zero to up. Okay. So at this point, we get it. Which one do you think is an insulator? The one with a very high gap is termed as insulator. Okay. And the one whose gap is between the conductor and the insulator is called the semiconductor. Okay. Then we have the conductor over here. Why do we say that? See, here we have electrons here, so it will become so difficult because they have a very big gap, right? It needs more energy to move from the valence band towards to the conduction band. So at times, insulators can conduct. At times, not always, but it's very difficult for an insulator to conduct. But if the voltage applied to an insulator is so high, do you get it? It can lose its property because at that point, if they gain the electrons gain a very high energy, right? Very high energy, which is very real, right? They can move from this side, the conduction band. So as soon as electrons from the insulator move from their valence band to the electron the conduction band, right? They begin to conduct, right? They begin to cause current flow. So it doesn't mean that they are insulated, so they cannot conduct. They can conduct, but they need a very high energy. So you need to apply a very high voltage in order for them to conduct. Secondly, this one too, before it can conduct, it need also some high energy, but compared to the insulators, they need quite little, right? the energy required for the electrons here to move to this side is bigger than the energy required for the electrons in the semiconductor valence band, right? But with the conductor, a little energy, it moves straight into what? To the conduction band. So that's the reason why conductors conduct what? Electricity easily. They causes electricity to flow easily compared to the insulators and the semiconductors, right? With the conductors, their band gap is not existing because the conduction band and the valence band, they overlaps. So because of that, a little what? A little energy or a little voltage which is applied to them causes the electron to quickly jump into what? To the conduction band. Okay, so that is it. It's so easy. Okay, so what our target is to know the conduction band, and we're able to compare the insulators, semiconductors, and the conductors in terms of what? The energy flow. Okay, and the movement of the electrons from the conduction or from the valence band to the conduction band. Do you get it? Yes. So that's it. So our next thing, the next thing that we are going to do is to compare the semiconductor atom to the conductor atom. So comparing, we are going to compare the semiconductor atom to what? To the conductor atom. Yes. So how are you going to compare it? See, let's take the silicon. So we are going to take the silicon as a semiconductor atom. So the number of atoms it has is 14. Silicon has 14 electrons. Okay. And we are also going to take the copper, right? Which also have 29 electrons. Okay. So according to Bohr's law, Bohr provided the formula. That is chemistry. I'm reminding you of certain stuff, right? So we said that filling the electrons, we have some formula for it. Okay, and it's given by 2n squared. Yes, so it's given by 2n squared. So in that case, if I should fill or if I should draw the silicon atom, let me draw the silicon atom here. So I have the first shell is 2n squared. So it's going to be 2 multiplied by 1 squared, which is what? 2, right? So at the end, the first shell is going to take 2. So we have 1, 2. What about the second shell? Sorry, the second shell. Let me draw the second shell. Very good. So the second shell is going to be 2 times 2 squared, right? Which is going to take what? 8. With the second shell, we are going to fill it with 8. So we have 1, 2, 3, 4, 5, 6, 7, 8, right? Then the third shell is 2 times what? 3 squared, which is going to be 18. But we are left with just 4. With the third shell is going to take how many? 4. Let me draw the third shell. Third shell and fill it with 4 electrons. 1, 2, 3, 4. We have the nucleus in here. Okay. So what about the copper? So with the copper 2, the first shell takes 2. The first shell takes 2. So we have 1, 2. And the second shell takes how many? 8. So we have 1, 2, 3, 4, 5, 6, 7, 8. Right. So we are left. We have 10 now. We filled it with 10, and it's left with how many? You left with 19. So the third shell takes 18. So let's draw the third shell. So the third shell will have 18 there. So we are going to fill it with 18. Let's move on. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Very good. And the last shell, you left with 1. So the last shell, what? Take the last one. Okay. So we are going to have 1 day. We have 1. Yes. Let's see something. There's a statement that the further the shell, the further the shell, the shell, right, the higher the what, the potential energy or the energy, any of them. Okay. So let me just use energy so that you not be confused. The higher the energy. Okay. So this is the energy that is required for the electron to move into what? Into the, how do you call it? The conduction band. So let's assume that we have the electron here. That is, this is the, how do you call it? The copper atom. The valence electron is having what? The valence shell is having 1 electron. So this is the copper atom. Right. Yes, and this is the silicon atom. Okay. So with the silicon atom, we are having what? We are having only 3 shells. Okay. So in that case, comparing these ones, the electrons are in the 3rd shell. You get it? And with this one, the electrons are on the 4th shell. So in that case, this one is having a higher energy to move from what? From the valence band to the conduction band. It has a higher energy. We discussed the band in our previous section. That is, we talk about the valence band and the conduction band. So I'm assuming that you understand what I'm doing over here. So you see, but this one, the energy it has, although it's also quite good, but this one has the highest energy. That is the reason why copper conducts easily compared to what? The silicon atom. So with this one, is because the further the shell, the higher the energy. So at this point, if we should compare the two of them, this copper will conduct or will move to the conduction band so quickly compared to the silicon atom. So we can make a conclusion that the copper atom can conduct faster than what? Than the silicon atom. Okay, the copper atom conduct easily compared to the silicon atom. So that's it for the comparison between what? The semiconductor atom and the conductor atom. Okay. So we also want to compare the two types of, or the two famous semiconductor materials. So we are going to compare the silicon which has what? 14 atoms, and we also compare the germanium which has 32, right? Germanium is having 32 atoms. Do you get it? So let me just focus on the outermost shell. So with the silicon, right, the outermost shell will have four, right, but it's going to be on what? On the third shell, right? And with the, how do you call it, with the germanium, this is, with the copper atom we have what? We have 14. So let's assume that this atom is germanium atom. So if I have the 29th year, then we will have what? 30, right? 30, 31, 32, right? So you can see that the germanium atom is occupying what? The fourth shell. So the outermost shell is the fourth shell. That is 1, 2, 3, 4. But this is what? This is the fourth shell and not the third. But we made a claim that the what? The further the shell, the what? The higher the energy, right? So in that case, we can say, let me write this as the germanium, right? Germanium and silicon. We can say that the germanium is what? Is unstable compared to the silicon. So germanium is unstable. Why are we saying that? It's unstable, right? Compared to silicon. Why are we saying it's unstable? It's unstable because, you see, it is having higher energy, so it can easily move towards to the conduction band, right? It can move to the conduction band with ease without any struggle compared to the hot, compared to the silicon. Silicon is on the third shell, so the energy is small compared to the germanium. So in that case, the silicon the electrons in the silicon shell is more stable, but the germanium, they are unstable, right? So it is unstable at a higher temperature. So if I should apply equal temperature over here to excite the electrons, this one will quickly move towards to the conduction band compared to what? Compared to the silicon electrons, the outermost shell of the silicon. So that one will be very difficult, right? If I compare the two, it will be quite difficult to move to the conduction band. But with this one, it will move there quickly at the same temperature. Okay. So we can make a claim that the germanium is unstable at a higher temperature, right? So the germanium, right, is unstable, right, at a higher temperature. A higher temperature, right? And it results in what? In excessive reverse current. So as soon as they become unstable, right, it leads to what? Excessive reverse current, right? And this is the reason why people prefer the silicon in making the semiconductor electronic components. Like, so it's because the silicon is more stable at a higher temperature compared to the germanium. So the germanium is unstable if we apply a higher temperature, which causes what? Excessive reverse current. And that is not the aim in making electronic components. So they always go forward for the silicon in in making semiconductor electronic components. Okay, so let's proceed. We are proceeding. The next thing that I'm going to talk about is conduction, electrons, and holes. So, conduction, electrons, and holes. Yes. So, with the conduction, electrons, and holes, let me draw the energy band. Right. Moving from a zero energy to a very higher energy. So let me draw the energy band here. So we have the conduction band. Conduction band. And also have the valence band or the atomos shell band. Right. So with the valence band, see there are electrons there. We have electrons at the valence band. Okay. So a little energy, the electrons move into what? Into they move from the valence band to the conduction band to conduct. So once they leave there, they leave a space there at the valence band. Okay. So they leave a space at the valence band. And that space is what is termed as hole. So that space here is what is termed as hole. So this is termed as the hole, and this is termed as what? Conduction electron. Conduction electron. Okay. So between the two of them is what is termed as the electron hole pair. Okay. So we have the conduction electron. Once electron move from the valence band to the conduction band, then it is called conduction electron. Okay. So when that electron leaves, it creates some hole here, and that is what is called a hole. So this is the conduction electron, and this is the hole, and the pair of them is called the electron hole pair. Okay. So that is all for the day. I'll encourage you to read page 25 to what? To 35. Yes, page 25 to 34. Sorry. Page 25 to 34 of the book that I've sent you. Right. So read page 25 to 34 and you get to understand the concept very well. I believe what I've said here, it makes sense to you. So try as much as possible to read the pages that I've given to you within the week. And I believe that once you read it, you understand very well. So we are going to end the video here, like I said. But in our next video, we will talk about the the PN junction. PN junction. But before even we talk about the PN junction, we will talk about the N-type semiconductor. Right. We talk about the P-type. Sorry, P-type. P-type semiconductor. Then we also talk about that is this one results in what? In the doping of the semiconductor materials. Okay. Then after we'll talk about the depletion region. Depletion region, right, of a PN junction. You get it. Then we also talk about the forward bias and reverse bias. We explain the forward bias and the reverse bias. reverse bias. Are you okay? We are going to talk about this once in our next video. But before we even talk about this, please, within this week, try as much as possible to read page 25 and 34. Very soon you see that we'll be moving to an exciting places where I'll be using the software simulations. Are you okay? So please try to read this before you watch my next video, else you will struggle to understand. It will be accumulating and you struggle to understand. Follow my videos. Are you okay? Don't wait. Just follow them and just do what I ask you to do. Before you come to school, you see that you have a fair knowledge, and when the lecturer is explaining, it becomes so easy for you. So please subscribe to my channel. Are you okay? Subscribe to my channel. I'm pleading with you. That's the only way you can use in paying me back. Are you okay? So subscribe to my channel, and I believe that you'll be fine. Are you okay? I wish you all the best and see you another time. Bye.